Hey, welcome guys to our subject, and for today we will be discussing the load combination and design of tension members of steel structures. So the outline of our module for today will be as follows: yung factors for Lrfd and Asd, and also the load combinations na ginagamit sa kanila. And then we will have yung design of tension members natin wherein discuss o pabalikan natin yung mga state limits o limit states na kinoconsider sa kanya, and then solve tayo ng example ng design. Okay, so at the end of this session, here are the learning outcomes that you should able to have. First one is to explain the factors used in Lrfd and ESD. Um, meron kayo ng background kung bakit yun yung ginagamit, bakit kailangan ganun yung value sa load combination, no? And then to define yung different load combinations natin for Lrfd and ASD. And then revisit yung limit states para sa tension members kasi as we know, you already discussed this dun sa principles of steel structures yung subject. So our case will be revisitation lang no, or reiteration lang ng mga limit states natin, and then diretso na tayo sa design ng tension member. Okay? So let's start first sa factors for Lrfd and ASD. So for Lrfd factors, if you check your NSCP 2015 section 502.3.3, nakalagay po doon na dapat to use yung Lrfd design philosophy, as we have discussed din last time. Dapat daw yung required strength natin is less than do sa design strength natin. Anong pinagkaiba ng dalawa? Yung required strength natin is galing siya sa loads, no? So ito yung um, acting or values taken from analysis na galing sa external loadings natin. Okay? Meaning the load, live load, and environmental loads. Okay? Then yung design strength natin, si design strength is yung capacity ng mismong section na dinesign natin. So dapat daw, syempre, dapat mas maliit yung strength mas maliit yung value nung mismong load dun sa member natin, kasi pag mas malaki yung load, syempre mag-fail yung member natin. So yun yung basic philosophy niya. And here we define yung required strength as summation of gamma I, QI, wherein yung QI is yung load effects tinatawag natin, and then yung gamma I is yung load factor natin. So in Lrfd, yung values ng mga yan, yung each load effect o yung QI natin has different load factor depending kung anong klase siyang loading. Okay? And sa load combination, meron makikita mamaya yung iba't ibang load effect o yung factor na ginagamit natin, which is yung gamma I. Okay? And then we have dun sa design strength side natin, dun sa capacity side natin, we have yung natawag nating resistance factor. So meron tayong meron tayong load factor, meron tayong resistance factor. Kaya nabuo si load resistance factor design, no? Kasi yung load natin is nire-reduce natin, and then yung load factor, yung design strength natin is meron din siyang factor. Okay? Okay, so Lrfd load combinations according to NSCP 2015 section 203.3.1. So if you check your NSCP, ito yung nakalagay sa kanyang load combinations, no? So where strength design or load and resistance factor design is used, structures and all portions thereof shall resist the most critical effects from the following combinations of factor loads. So ito din yung ginagamit natin for concrete na USD, no? Ultimate strength design. So same siya ng values. Kaya lang sa steel, hindi lahat ng loadings natin are applicable. What do I mean? Yung halimbawa yung fluid pressure na F, yung value, yung F, yung H para sa earth pressure, and then yung self-straining force na T. Okay? So all of those loadings are not applicable to the design of structural steel members. Kaya mas convenient na i-simplify natin yung load combinations into the following. Okay? Ayan. So, ito yung simplified. So, meaning, ito yung ginagamit for steel. Okay? So, ang meron lang dito, we have dead load, live load, roof loading, yung LR, and then rain load kung meron, yung R, then wind load, and then earthquake. Okay? Then for F1, you have here a notation or note na for floor or in places of public assembly, 1.0 siya, or for live load in excess of 4.8 kPa, and for garage live load, okay, 1.0 siya, and then 0.5 siya for other live loads. Okay, so ano yung mapapansin ninyo dun sa loadings natin? So yung sa load factors natin, makikita ninyo, nag-iiba yung value ng mga loadings, yung factor kada loadings. Let's say, dito sa first one, yung dead load natin, in-increase natin yung value ng actual load na yun ng 1.4. So, ibig sabihin, siya yung nag-govern, yung maximum siya at that load combination. Okay? Dito, sa second load combo natin, ang highest natin ngayon is si live load. Okay? So, ibig sabihin nito, ina-assume natin na si live load, si dead load, si live load, tsaka si roof live load will act at the same time sa structure natin, and ang kino-consider nating maximum sa kanya or nag-govern sa kanya is si live load. Kaya makikita mo, ni-reduce na yung sa dead load. Okay? And yung sa roof live load is reduce din yung value niya. Ano naman kaibahan ng load combo number 3? Sa combo number 3, makikita nyo yung roof live load naman yung times ng 1.6. So, ibig sabihin, si roof live load naman yung maximum dito sa number 3. Okay? Siya yung, kumaga, yung tinatawag nating lifetime maximum. Okay? Sa load number 4, ito na, meron tayong wind. And then, ang maximum sa kanya is si dead load pero with wind tayo na 100% ng wind. Okay? So, yan yung consideration niya. Then, same as dito sa earthquake. Okay? So, ngayon, dito sa number 6, magtataka kayo. Bakit naging 0.9? Ay, akala nga natin, di ba, gusto natin pataasin yung mismong ano natin, loading natin. Ba't dito parang babawasan pa natin? Do you have any idea? Kasi ano ba nangyayari pag ano, halimbawa nag-act yung lateral load natin. Halimbawa ito yung structure natin, no? Tapos may nag-act tayo na mapa-wind or earthquake. Ano bang tendency ng structure natin? Diba, mag-sway siya papunta dito, no? Mag-sway siya papunta doon. Okay? So, ibig sabihin, nagkikreate ng overturning moment. Okay? Ng overturning moment, yung mismong lateral load natin. And saan ba nakabase yung lateral load natin? Diba nakabase siya ay sa dead load nung mismong structure natin. Dependent siya dun sa weight. Okay? So kung nag-calculate ka dun sa halimbawa, kung sa thesis nyo nag-calculate kayo ng loading ng wind load tsaka ng earthquake, makikita ninyo na dependent siya dun sa weight. Yung pressure na consider natin, depende siya dun sa weight. Okay? So, ibig sabihin kapag ganito yung nangyayari, portions of nung dead load is ang gusto niyang gawin is to stabilize yung structure. Okay? Kaya ibig sabihin hindi lahat ng dead load are converted or nakakatulong na i-overturn yung structure natin. Yung iba sa kanila are working together to stabilize the structure. Kaya dito, pag meron tayong wind tsaka earthquake, hindi mo pwedeng taasan yung value ng dead load. Kasi kung tataasan mo pa yung value ng dead load, parang ano naman, no? Napaka extreme cases na yon. Okay? And then for load 5 and 6, yung possibility ng dead load and wind load counteracting each other. Okay? So kaya may plus minus kasi both side pwede magkamero ng no, pwede silang magtulungan, pwede silang mag-counteract o i-resist nila yung pwersa nila kaya may plus minus siya. Okay? Pero in each combination, sabi ko nga kanina, one of the effects is considered at its lifetime maximum. Okay? So may governing sa kanya. And then yung iba sa kanya is arbitrary lang nung earthquake niya. Halimbawa, nung nagka-earthquake, kung 100% yung earthquake na gagamitin mo, syempre, assume mo na yung dead load mo will not uh, be responsible lahat, no? Para tulungan yung earthquake. So yung iba doon will help the structure retain its stability. Okay? And then for LRFD resistance factors, the resistance factor P for each type of resistance is given by AISC and also can be seen on Section 502 to 511 of NCP 2015. But in most cases, one of the two values will be used. 0.9 for limit state involving yielding or compression buckling, and then 0.75 for limit state involving rupture or yung fracture. Okay? So ito lang yung dalawang karaniwang fee na ginagamit natin for LRFD para dun sa design strength natin. Okay? O yung capacity strength natin. And then next we have, so yun yung sa LRFD. Now we have yung ASD safety factors naman. Okay? So kay ASD, same principle din. Yung required strength is less than dun sa allowable strength natin. Pero si ASD, as we have already discussed before, yung sa loadings niya, wala siyang factor. Wala tayong minumultiply sa kanya na load factor. Okay? Pero yung sa ating nominal strength, nung mismong yung capacity strength ng material natin, dinidivide natin siya ng safety factor na omega. Okay? And pag divide natin yon, yung nominal natin, divided by nung omega, we have our allowable strength. Okay? So, kaya meron tayong allowable strength. So, ito shortcut to simplified na. Okay? So, meaning, inalis na yung fluid pressure for soil, inalis na. So, ito na yung for, for steel structures lang. Okay? So, mapapansin nyo sa load factor natin, bakit may 0.75, ba't may 0.6, ba't may 0.7? Eh sabi nga, di ba, yung load factor natin yung ASD natin, dapat yung load natin, walang factor, dapat full siya, no? Pero yung 0.75 dyan, is ginawa ng code kasi parang unlikely na magsasabay-sabay na mag-access ang structure yung loading na yun. Like for example, dito sa number 4 natin, yung sa live load tsaka yung sa roof live load natin, parang impossible na mag 100% sila ng sabay. Kaya nire-reduce natin siya ng 0.75 to account for the unlikelihood na yung loads na yon will be at their lifetime maximum simultaneously. Okay? Same with dito. And yung sa earthquake naman, kaya may 0.7 yung sa earthquake. Yung analysis kasi ng earthquake is based from load factor na. So para to equalize yung effect para sa ASD, si code is nag-introduce siya ng 0.7. Okay? So yan yung ginagamit for ASD. And then we have here yung ASD factors natin. Yung yielding or compression buckling natin, 1.67 naman yung omega natin kasi dinidivide natin yan, di ba? And then for rupture or fracture limit states, we have 2.0. Okay? So later, gagamitin natin yung mga factor na yan para dun sa limit states ng tension member natin. Okay? Now, we can now proceed sa design of tension members. Okay? So as a recap, tension members are structural elements that are subjected to axial tensile forces. Okay? So structural members that frequently appear as tie rods to stiffen a truss floor system or to provide intermediate support for a wall girth system are called tension members. So ito samples lang ng mga ginagamit yung tension members natin, no? So for roofing, meron tayong tie rods, no? Okay? Then yung rafters natin kasi di ba sa trusses lahat axial load lang tayo. Okay? Suspenders natin, we have yung sag rod natin. Okay, yung ilalagay natin sa purlins, no? Para hindi siya gumalaw. Then we have stay cables, suspenders, bracings. Okay. Yeah. So, yan lang yung mga ilan sa example ng tension members. Okay. And then si tension members, may limit states tayong tinatawag sa kanya. So the strength of a tension member may be described in terms of limit state na nag-govern sa kanya. So the controlling limit state for a tension member will be one of the following. We have yung yielding ng gross section natin, gross cross section. We have yung fracture ng effective net area, and then black shear fracture through bolt holes. Okay, so isa-isa natin. So we have first yung yielding of cross section. So if you check your NSCP 2015 section 504.2 item number 1, yung formula will appear dun sa NSCP, no? So um, let me check na kung naka-tab sa akin. Okay, so let me share to. Yan, so ito yung sa NSCP. So yan, 504.2 item number 1. So ito yung formula niya. We have Pn is equals to FYAG. So for our discussion, we will just use T sub n for tension, no? Para ano tayo. And then mamaya for rupture, we have itong FUAE. Okay? So going back to sa slide. Okay? So yan. So same formula to. We have yung ating nominal strength na Tn is equals to Fy times Ag, wherein yield stress yung Fy, and then yung Ag is para sa gross sectional area natin. So si Fy, depende kung ano nakaspecify sa problem, kung anong type ng steel yung gagamitin para sa kanya, no? And sa code, meron yung table. Okay? So I've asked you to download yung educational reference natin. So later, papakita natin kung saan pwede makita yan, no? Then for Lrfd, ito yung magiging condition natin. So since yielding yung condition natin na una from our previous slide, di ba dito nakalagay? Ayan, yielding, pag-yielding 0.9 tayo. Okay? Kaya makikita nyo dito sa ano natin, naka 0.9 yung ating resistance factor dito. Okay, so FYAG, dapat greater than siya doon sa T natin, doon sa ultimate load natin from load combination. Okay? And for ASD, pag niload natin ng safety factors natin, dapat greater than siya doon sa allowable strength, which is galing din sa loadings natin. Okay? Next, we have yung fracture of effective net area. Section 504.2 ng item number 2. So when the limit state is a localized yielding, resulting in a fracture through the effective net area of a tension member having holes, the nominal strength Tn may be expressed as Tn is equals to Fu times Ae, wherein yung Fu is yung specified minimum tensile strength, which is may table din po ito. Later, papakita natin. Then we have Ae, effective net area, ang formula niya is U times An. So yung U is called reduction coefficient, and then An is called as net area. So si net area and reduction coefficient tsaka sa effective net area, kailangan natin siyang discuss separately, no? Pero I hope na-discuss siya before sa inyo, yung principles of steel structures niyo. Pero dito lang since fracture na tayo, naging 0.75 na siya. So dapat greater than doon sa ultimate load natin. And then dito yung safety factor natin, dapat greater than doon sa allowable natin. Okay? So yung net area natin muna from NSCP, section 504.3.2. So when a tension member is to be fastened by means of bolt or rivets, okay, so sorry, rivets to. Holes must be provided at the connection. So as a result, the member cross-sectional area at the connection is reduced. So as a general rule, hindi siya dito naka-indicate sa NSCP, no? If yung diameter of holes yung given, ang gagawin natin kung ano yung given na diameter ng hole, plus tayo ng 1/16. So in inches po itong mga ano natin. Okay? So bakit in inches yung ba't English yung ginagamit natin? Since yung reference na design construction manual ni AIS is naka-base sa English system, usually English yung ating ginagamit na dimensions and unit natin. Okay? So 1/16 inches to. And then kapag diameter ng fastener yung given, 1/8. So to demonstrate this, we have here a simple example. Pinapahanap what is the net area, AN, for the tension member shown. So ano bang itsura ng tension member na yan? So pag dinrawing natin yung tension member na yan, ganito po yan. Ano? Yan ay plate. Okay? So may thickness yan, tapos may butas daw siya doon. Okay? So, um, okay. So, assume natin na ayun yung butas. Okay? So, yun yung itsura niyan. Then, may nakalagay dito, standard hole for a 3/4 inch diameter bolt. So, since diameter ng bolt yung given, para ma-identify natin yung net area natin will be equal sa yung area gross natin. So, ibig sabihin yung full section natin. Pero ano ba yung area yung kino-consider natin? So, as a review, iba tension yung ating force na naka-apply. So kapag yielding ng cross-section, yung ang kino-consider natin is yung stress niya dun sa face niya o dun sa cross-section niya. And ano ba yung cross-section na yun? Ito po yung cross-section na yun. Okay? Yan po yung nai-stress sa kanya. Okay? Kaya pag may presence ng hole, nare-reduce yung strength niya kasi nababawasan yung pumipigil dun sa pwersa natin. Okay? Kaya anong nangyayari, ito na lang yung nag-a-act na effective sa kanya. And yun, kailangan natin i-calculate yun. Okay? So, mula dito, again, ito yung gross area natin. Okay? Ito yun, AG. And ano yung gross area na yun? So, okay. Okay. Tawagin natin to yung thickness niya. And then, itong width na to is yung ating width. Okay? So, anong given? 1/4 by 4. Okay? So, syempre yung 1/4 yan is thickness, no? May plate tayong 1/4 by 4. So, ibig sabihin, 4 yung width niya, 4 inches. And then, meron siyang thickness na 1/4 or 0.25. Okay? So, pag pinapahanap yung effective, yung net area, minus lang natin yung area nung hole. Okay? Or nung diameter. Okay? So, equals na lang yan sa anong value nito, yung AG niya nung una. So, rectangle lang naman yan. So, width times height lang. So, 4 times 0.25. Ma-minus natin. Ilan yung bolt natin o yung given na bolt? Isa lang. Okay? So, kung isa lang ibabawas natin. Okay? Minus 1. Tapos yung diameter natin is 3/4. Since yan ay bolt, ito tayo, dB plus 1/8. Okay? 1/8. So, ito pa lang yung bagong width natin. Okay? Yung reduced width na to. Times natin ang thickness na 0.25. Matitira, ang net area natin is 4 times 0.25 minus 1 times 3/4 plus 1/8 times 0.25. So, we have how much to? 1/4 minus 1 3/4 plus 8 times 0.25. Okay, so 0.78125. Okay? So, yun na lang yung area na titira sa kanya. Okay? Yung gross area niya is 4 times 0.25, 1 inch squared yung gross area niya. And then, dun sa presence nung ating mismong diameter na bolt, naging na lang siyang 0.78125. Okay? So, kapag ginamit natin yung formula ng sa fracture, ito yung gagamitin natin for AN. Pero kailangan natin ay U times AN or yung A yung need natin. So, kailangan pa natin identify yung U. Okay? So, si U is makikita natin yan ay sa ating sa code, no? So, si NACP tsaka si AISC may value niyan. So, let me display. Kay NSCP muna. So, kay NSCP, yan is, ang tawag niya is, ayan, um, table 504.3.1, shear lag factor for connections to tension members. So, ito yung table na ginagamit dyan. So, may depende sa case natin, yan yung ginagamit na value ng U. Pero nakalagay naman yung definition. So, we have case 1. So, i-check mo siya isa-isa, no? Meron directly, and then meron dito, transmitted to some but not all. So kapag halimbawa, may yung portion lang nung na may drawing naman, ayan no. Ibig sabihin dito, yung flange lang yung naka-connect pero yung web hindi naka-connect kaya ginamit niya yung formulang to. Okay? All tension members where the tension load is transmitted by transverse weld. So kung may welding, so hindi mo pa to. Ang check mo lang dito kapag tension members, itong number 8. 7 or 8, depende sa material. Kung halimbawa, W section ang ginamit, check mo tong conditions na to. And then pag angle yung ginamit, ito yung gagamitin nating value. Okay? Pero yung value nun will be based from this table. Okay? And then from AISC, yan, sa AISC, yung table na yan is ito. Okay? So same values naman siya. So inadapt lang ng NSCP from AISC. Okay? Ayan. So let's go back dun sa slide natin. Okay, now yung effect naman ng staggered holes on net area natin. So whenever there is more than one hole and the holes are not lined up transverse to the loading directions, more than one potential failure may exist. The controlling failure is that which gives the largest stress on the effective net area. So ibig sabihin, kailangan mong i-analyze ngayon yung mga iba't ibang path na pwedeng mag-break yung yung tension member natin. Okay, kung paano siya mapunit. Okay? So kapag mga staggered yung connection natin, di ba ito yung standard connection natin, yung usual na tearing niya o pag-rupture niya is itong along dito. Okay? So walang problema yan. Mas madaling i-compute yan kasi ang gagawin lang natin, yung AN natin is equals to AG minus dalawang area ng hole. Okay? Pero pag staggered na siya, iba na yung case. May i-consider ka ng mga path, no? So, anong isang consideration? Pwedeng ito yung maging punit ng member natin. Pwede din siyang mapunit along dito. Bawa, yan. Ito. Tapos, yan. Okay? And yung effect na yan, yun yung tatawag natin staggered. Okay? Na ina-add natin dun sa ating net area. Okay? So dito, para makalculate yan, so pag ito yung kinonsider natin, yung first one, yung same formula lang nito, so isa lang yung nadaan ng butas, so minus AH lang siya. Okay? Tawagin natin yung red as AB, and then yung black as A, C, D, E. Okay? So yung path AB natin, ang AL niyan will be AG minus AH lang. Pero pag yung A ay yung CDE, yung AN natin will be equals to AG minus kung ilan yung holes. So meron tayong 2 holes. And then plus yung ating staggered na S squared over 4G. Ano yung S? Ano yung G? So yung S natin is ito. Wait lang. Baguhin ko yung kulay. So yung S natin is ito. Then yung gauge natin is ito. Okay? So kung ano yung center to center distances nila, value. Then substitute mo lang siya dun sa formula mo ng AN, makukuha mo na yung net area mo. Then para maging effective, multiplied lang siya by the reduction factor galing dito sa itong reduction coefficient natin na yun dun sa table. Okay? So, next, ano bang kasunod natin? So, next we have yung block shear. Saan tayo? Effective net area. Okay, so effective net area. So, the reduced section calculated for AN may still not correctly reflect the strength. Kaya kailangan pa natin siyang i-reduce yung U natin. Okay? So, this is particularly true when the tension member a profile consisting of elements not in a common plane. So, ibig sabihin, nabawa yung angle natin. Di ba, usually ang angle natin, bawa ito yung angle bar natin, ang kinakabit lang natin halimbawa sa, bawa ito yun, no? Kinakabit lang natin sa kanya is ito lang, yung isang leg lang niya. So, ibig sabihin, hindi, yung buong capacity ng structure, hindi naman siya talaga lahat nabawasan. Okay? So, o kaya yung binawas natin is not enough kaya kailangan pa natin siyang i-reduce further. Okay? Na ito yung mga tables na pinakita ko kanina. Okay? Then next is block shear strength. So si block shear nangyayari siya yan for certain connection configuration, a segment or block material at the end of the member can tear out and this phenomenon is called block shear. So, halimbawa, nag-apply tayo ng tensile load dun sa mismong angle natin. Ito yan, angle bar natin. Pwede siyang mag-tearing ng gantong direction, no? So, pwede siyang mag-shear. And then, meron din siyang included na tensile um, na failure. Okay? So, yung combination ng shear tsaka ng tension. So, shear kasi yung area na nare-reduce sa kanya ay along din dun sa length sa applied load natin. Kaya shear yung tawag and then iba dito yung stress natin, yung actual stress natin kapag naka-transverse siya o naka-perpendicular siya dun sa load natin. Okay? Kaya yung code pag chinek natin, may formula siya na for example pag gusset plate or angle plate yung ano natin, ito daw yung formula. So combination siya ng shear and yung ating tension area. Okay? So, chine-check lang natin yung first term dito sa limit na to. Okay? Whichever is greater. Kung mas nag-govern to or kapag na greater than yung value nito dito, ito na yung gagamitin nating minimum na value sa kanya. Okay? So, for other members, nagbabago lang yung factor niya dito sa second term. Okay? So, pag chinek natin to sa NSCP, this is section 510.4.3. Okay? So, pakita ko lang sa NSCP. Okay, and then NSCP tayo. Block shear. Okay, yeah. So, block shear strength 510.4.3. Pag nakita niyo, na-check niyo yung formula, ito yung formula niya. 0.6 FUANV plus UBS. So, may UBS siya. So, yung UBS may definition dito. 1 siya kapag uniform yung stress and 0.5 siya kapag non-uniform. So, same values, same factors, safety factors. Yun lang yung section na kinonsider. Okay? Again, going back dun sa ating Slide. Okay, so for LRFD, sinusunod natin yung sa rupture na limit state na factor na 0.75. And then for ASD, we have 2.0 para sa rupture. Okay? Dapat cater din siya doon sa ultimate load and doon sa allowable load natin. Okay? Next, now we can go doon sa design of tension members natin. So the design of tension members involves finding a member with adequate gross and net area. So ibig sabihin ito yung mahalaga pa nagde-design tayo. Ang unang chine-check is hinahanap natin yung minimum na gross and net area nung system natin. Kasi pag design, tayo yung magde-decide kung anong size ng member yung gagamitin. Okay? From the applied loads, mula doon, i-identify natin yung value ng areas. Then after natin makuha yung areas, ang kasunod daw is, secondary consideration natin is yung slenderness niya. Okay? Although hindi required by the code yung slenderness, pero may user note kay AISC Construction Manual na sinasuggest niya na dahil ang mga tension members are usually prone to vibrations, maganda i-limit din natin yung slenderness niya. And yung limit na binigay niya ng L/R, yung slenderness ratio natin is dapat less than or equal to 300 lang. Okay? So take note na hindi po siya nag-a-apply sa cables or rods. Okay? So ito suggestion lang naman ni AISC. So pwede siyang pwedeng mag-exceed pero with assurance na tama yung calculation natin. Okay? Alright, so for tension members design by Lrfd, so ito yung formula natin. Pinagbaliktad ko lang. So, hindi pa pala baliktad to. So, gagawin natin, kailangan natin is yung AG. So, pwede natin divide both side by 0.9 Fy, 0.9 Fy. So, pag hinahanap natin is LRFD, kailangan yung AG natin is greater than TU over 0.9 Fy. Wherein yung TU natin is yung ating governing load. Okay? From our load combination. Okay? And si Fy, okay, si Fy, meron din pakita ko din yan. Kay AISC, depende sa grade ng material o kung anong ginamit na steel. So meron siyang table, table 2-4. Makikita nyo dito, halimbawa sinabi, 836 yung material na ginamit. Yung value ng Fy niya is 36 KSI. And then yung tensile stress niya is 58 to 880, no? Pero tayo pag may range na ganito, ang kinukuha nating value is yung lower bound tayo. So 58 KSI. So halimbawa, A572 na grade 50 yung ginamit na material. Ibig sabihin 50 KSI yung yield stress niya. And then 65 KSI yung kanyang tensile stress. So i-tab nyo na lang dun sa AISC na copy ninyo kasi hindi yun nakatab dyan. No? Okay? So, okay, going back to sa lecture. So, pag nakuha natin yung gross area natin, ang next nating kailangan i-check is yung kanyang net area. And yung net area natin is manggagaling siya dito sa formula natin para dun sa fracture, no? So, ito, para makuha yung effective area, okay? So, 0.75 FU, 0.75 FU. Okay? Cancel out. So, ang required na effective area natin, effective net area, is dapat TU over 0.75 FU. Okay? So, same din, governing load yung TU. Then, yung 0.75 is factor for fracture. And then, yung 0.9 is for yielding. Okay? Next, for ASD, same lang din. Ito, baka malito kayo, yung 1.67, so dinivide lang. Divide nyo yung 1 over 1.67 equals sa 0.6. Kaya yung 0.6 ang nakikita usually sa code, no? Pero same lang yan. It's actually 0.59 something something. So, rounded up sa 0.6. So, kunin lang natin yung 0.6 FY, 0.6 FY. So, yung area gross natin for ASD, dapat yung allowable load is divided by 0.6 ng FY. And then dito, 0.5 naman. So, 1/2, no? Kaya 0.5. Cancel, no? So, yung effective area natin should be greater than the allowable all over 0.5 FU. Okay? So, yan yung kailangan nating una i-calculate. And then, ang kailangan natin identify na kasunod is yung L over R natin na dapat siya ay less than or equals to 300. So, kung i-interchange natin, dapat is yung L over 300 natin is less than or equal sa R natin. Okay? So, R minimum to, ibig sabihin. Okay? So, yan lang yung criteria for tension members. Ngayon, para mas maintindihan, apply natin sa design talaga ng may loadings na tayo. Okay? So, let's start with the first one. Okay. So, a tension member with a length of 5 feet 9 inches must resist a service dead load of 18 kips and a service live load of 52 kips. Select a member with a rectangular section. Use A36 steel and assume a connection with one line of 7-inch diameter bolts. Solve using Lrfd and Asd. Okay? So, both methods para to compare yung solution. Okay? Lrfd muna tayo. Okay? So, given natin we have a length na 5 feet 9 inches. So, yung 9 inches equivalent niya sa feet is 0.75. So, that is 5.75 feet, no? So, yun yung length natin. Then, we have a dead load na 18 kips. Live load na 52 kips. And then, yung property natin is A36 yung steel. So, pag tinignan natin yung table, yung Fy natin is equals to 36 KSI. Fu natin is equals to 58 KSI. Okay? And then, meron tayong 7 diameter ng bolt. Okay? Na 7/8. Okay? So, pinapadesign tayo ng rectangular cross-section. So, ibig sabihin, pwedeng plate or bar siya, no? Ang itsura niya, so siguro top view to. Okay? Ito yung top view niya. Then, meron tayong applied na tensile load sa kanya. And then, pag tinignan natin yung kanyang cross-section, mag-pass through tayo ng cutting plane. Yung cross-section niya should be a rectangular section. Okay? So, dapat meron tayong thickness and then meron tayong width. Okay? So, yan. So, tapos meron siyang one line of 7-inch. So, sabihin natin meron siyang ganyan na mga, kasi wala namang sinabi na kung ilan. So, pwedeng assumption lang na ganyan. Halimbawa, may 4 na bolt. Pero, hindi yan, hindi naman sinabi. And hindi naman importante kung gano'ng kadami. Kasi kailangan natin is yung isang portion lang. Okay? Yan. So, ito na yung given natin. Pwede tayo mag-calculate. So, yung first step natin is to calculate for the ultimate load. Okay? So, ultimate load muna tayo. Yung TU natin. Okay? So, from load combination, meron tayong dalawa pwedeng gamitin. We have 1.4 DL and then meron tayong 1.2 DL plus 1.6 LL. Okay? Check nyo na lang ulit to sa previous slide. Or, sige, pakita ko din. This one. Okay? So ito hindi nakasulat pa tayong roof live load, wala tayong wind, wala tayong earthquake. So itong dalawa lang yung pwede natin gamitin. Okay? Uh, okay, then calculate 1.4 nung dead load natin. So 18 kips. So how much yun? So 1.4 times 18. That is 25.2. Dito, substitute ko na diretso. 1.2 times 18 plus 1.6 times 52. We have 104.8 kips. So, ibig sabihin, ito yung nag-govern, no? So, ibig sabihin, TU natin is equals to 104.8 kips. Okay? Next. Next natin is calculate for AG tsaka AE. Okay? So, using lang yung formula natin for yielding tsaka sa rupture. Okay? Sa fracture. Okay? So, una, AG should be greater than TU over 0.9 FY. Okay? Galing yan dito sa previous slide natin for LRFD. Okay? So, equals yan sa 104.8 kips all over 0.9 tapos 36 KSI. Okay? So, matitira pag dinivide, that is 3.234 inch squared. Okay? And for AE natin, that is TU over 0.75 ng FU. So 104.8 kips lower 0.75. Then FU natin is 58 ASI. So that is 104.8 divide 0.5 times 0.75, sorry. It's 58. We have 2.409 inch squared. Okay? So meron na tayong AG tsaka AE na minimum. Okay? Dapat yung makalculate natin are greater than those values. Okay? Next. Ang next condition natin is to get yung ating slenderness ratio. Okay? So, yung atin is L over R. Dapat ay equal siya sa, walang may binanggit ba? Wala. 300, no? Less than or equal to 300. Pero pwede nga natin makuha na yung minimum na R natin will be equals to L over R. Okay? So, meron tayong 5.75 feet. Gawin natin inches over 300. So, yung R minimum natin should be 5.75 times 12 over 300. That is 0.23 inches. Okay? Yeah. So, meron na tayo ng tatlo. Ngayon, pwede na tayong mag-design. So, pwede gamitin natin yung values ng ating gross section. So, since rectangular yung required sa atin, mas madali, no? Kung ito yung gross, pwede tayo makakuha ng width niya kung mag-a-assume tayo ng thickness niya. Okay? So, ano ba yung mga thickness na pwede? So, kapag thickness ang pinag-uusapan sa plates, so pag plates ang thickness, dapat increment siya ng 1/8 inch. Okay? Ng 1/8 inch. Pero assume na lang tayo ng medyo malaki na, no? So, halimbawa, assume thickness na 1.0 inch. Okay? So, using yung AG natin, dapat greater than sa 3.234. Since yung section natin is ganito yung thickness, ito yung W. So, kung thickness natin is 1, okay, equals dun sa WT. Tapos kung gagawin natin itong 1, so yung W natin will be equals to 3.234 or greater than dapat siya sa 234. or inches, or say natin, halimbawa, is yung width dapat is increment siya ng how much? Ng 0.25. Okay? So, since ito 0.23 na, so parang kukunti masyado pag 0.25, 3.25 gagamitin. Say natin na 3.5 inch. Okay? So, kung 3.5 yan, yung ano natin, try plate tayo na 1 inch by 3.5 inches. Okay? So, ano yung kunin natin yung property niyan? Plate na 1 by 3.5. Okay? So, ito yan. 1 inch. Then ito is 3.5. So, yung area gross niyan will be 1.0 times 3.5. So, area gross is 3.5 inch squared. Okay? So, ito is greater than dun sa AG natin. No? So, okay siya doon. Okay? Check natin sa AE. Okay? So, kung may dadaan sa kanyang isang line, okay, ano yung effective niya? Okay? So, yung effective natin, so, kunin natin yung AN equals AG minus whole natin. Okay? So, ito yun. So, AN is equals to AG minus area ng whole. So, equals sa 3.5. Yun yung nakalculate natin AG niya. Minus yung area ng hole niya will be isang hole times yung size natin is 7/8. Tapos since diameter na siya, 1/8 yung ipa-plus natin times yung assumed thickness natin na 1 inches. Okay? So yung AN natin dito will be 3.5 minus 1 times 7/8 plus 1/8 times 1. Okay? So we have 2.5 na value. Okay? Tapos yung area effective natin, dapat U times AN pa siya. Pero since walang binigay na given kung saan siya naka-connect, no? Kasi pag check natin yung table, okay, check natin yung table. Okay, then check natin yung shear log factor. Okay? So, hindi sinabi kung saan siya naka-connect na plate. So, hindi natin pwede gamitin tong formulang to. So, hindi siya naka-weld, hindi pwede to. Hindi siya W shape. Okay? Hindi din siya angle. So, dito na mag-fall under sa case number 1. All tension members where the tension load is transmitted directly to each of the cross-sectional element by fastener or weld. No? So, yung U natin is equals to 1.0. So, yung AE natin for our example number 1 will be equals dun sa ating value ng AN. Okay. Times 2.5. So, AE natin is equals to 2.5 inches squared. Okay? Pag chinek natin yung AE, ang required natin is 2.409. So, greater than yung nakuha natin. Greater than siya dun sa value na 2.409. So, ibig sabihin okay siya doon. Okay? Ngayon, check natin siya sa slenderness. Okay? Paano natin makukuha yung slenderness? Kailangan kunin natin yung sa section natin. Ang slenderness device L over R. So, ang L natin, calculated natin kanina na 5.75 times 12. Okay? Yung R natin is kailangan calculate natin. Ang radius of gyration from our lecture yesterday, I over A siya. Okay? So, pwedeng maging R is equals to square root of I over A. So, ibig sabihin, square root, tapos yung inertia niya, which is minimum dapat, no? So, dapat yung naka-cube yung maliit, mas maikli. 12 times yung 3.5 na area natin. Okay? So, ano yung magiging value? 5.75 times 12 all over square root of 3.5 times 1 cube all over 12 times 3.5. We have 239.023 which is less than 300 which is okay also. So pag nag-okay na siya dun sa tatlo, sa gross, sa effective, tsaka dun sa slenderness natin, pwede natin conclude na use plate na ang size is 1 by 3.5. Okay? So, pwedeng ito na yung gamitin natin. Okay? Pero paano kung di mo naisip na 1 inches yung assumption mo? Diba? Siyempre, di man tayo lahat experience na mag-design. Okay? What if, halimbawa, ang inassume mong thickness, assume ka ng thickness, no? Assume ka ng thickness na, halimbawa, siyempre yung reasonable na thickness. Pag mga plate, hindi naman masyado lumalaki yan ng, ano, no? Sobrang kakapal. Okay? Kasi nagmamahal ng, ano yan. So, halimbawa, inassume mo is 0.5 inch lang siya. Okay? So, kung 0.5 inch siya, so yung AG natin is equals to 0, ngayon, 3.234. 3.234. So, equals sa WT natin. So, W times 0.5. Ibig sabihin, yung width na makukuha natin is equals to 3.234 divided 0.5 is 6.468. Okay? So, ito yung section natin. 0.5 tapos siya ay 6.468. Okay? Next, yung gross area niyan will be 6.468 times 0.5. Hindi. Dapat wala magsasay tayo, no? Kasi yan ay width. So, gawin natin sakto. Inches, say natin na 6.5 inch. Okay? So, ay 0.5 and then ito ay 6.5. Okay? And then, i-analyze natin siya na meron siyang butas na isa. And then, meron tayong applied na tensile force. Okay? Dito, yung area gross niya is 6.5 times 0.5. That will be equal to 6.5 times 0.5. So, 3.25. Of course, greater than yan dun sa gross required natin, no? Then, yung, para makuha natin yung effective, so, A is equals to UAN. So, assume natin na nalaman natin na 1.0 na siya. Then, yung AN natin will be gross area natin na 3.25 minus 1 whole. Yung whole natin is 7.8 plus 1.8 times yung thickness natin is 0.5. Okay? So, ilan yung magiging value ng AE natin? 1 times 3.25 minus 1, 7/8 plus 1/8 times 0.5. Okay? That will be 2.75. Okay? So, na. Okay? 2.75. So, greater than siya do sa AE natin na 2.409. So, okay tayo. Check natin sa slenderness. Okay? L over R. So, we have 5.75 times 12. Then, yung R natin will now be equals to square root ng inertia muna tayo. So, 6.5 times 0.5 cube all over area. May 12 tayo dito times yung area natin na 3.25. Okay. So, 5.75 times 12 over square root of 6.5 times 0.5 cube over 12 times 3.25. So pag kinalculate natin yan, slenderness ratio natin is 478.046, which is greater than 300. So hindi not good na siya. Okay? So ibig sabihin kailangan mong reiterate yung design. Na eventually, makikuha mo si 1.0 yung pinaka minimum na pwede. Okay? So iterative process tayo pag design. Okay? So kung nagka-calculate kayo, pwedeng gumawa kayo ng Excel, no? Para trial and error. Every time na hindi okay dun sa isang criteria based from the three, yung AG, AE, tsaka slenderness natin, pwede kayo mag-assume ng thickness kapag rectangular yung cross-section natin. Okay? So ito yung solution pag LRFD. Okay, question before i-solve para sa ASD? Okay. So ngayon ASD tayo. So let's try ASD. Okay, so sa ASD, syempre magbabago yung value ng AG, AE, tsaka nung load natin. Okay? So ultimate load natin, so dalawa lang din naman yun, D tsaka D plus LL. No? Pero syempre, mag-govern yung pangalawa kasi additive ng dalawang value yun. Okay? So ito ay 18. So 18 plus 52. So this is 70. Okay? Next, yung AG and AE natin. So AG, kapag sa ASD, ang gagamitin natin is ito na, TA over 0.6 FY. So this is our TA, no? TA over 0.6 FY equals to 70 kips all over 0.6 times 36 KSI. 70 over 0.6, 36. We have 3.241 inch squared. Then AE, we have TA all over 0.5 ng FU. So 70 divide 0.5 times 36 KSI kips. 70, 0.5, and then 36. Hindi pala 36, 58. Kasi FU tayo. Okay, so we have 2.414 inch squared. Okay. Then next is try na tayo. Try ng thickness. Sige, 1.0. Try natin 0.75. Okay. So kung 0.75 yun, yung area gross natin, 3.241 is equals to WT. So W times 0.75. Okay. So W niyan, pag kinalculate, 3.241 divide 0.75, that is 4.321. Okay? Inches, say natin na 4.5. Okay? So yung section natin will be like this. Thickness natin is 0.75 and yung width natin is 4.5. Okay? Ang area gross niya ngayon will be 4.5 times 0.75 times 0.75. That is 3.375 inch squared. Of course, greater than the sa required AG natin. Then ang area net natin or yung AE natin, okay? So AE will be equals to U times AN. So ito 1.0 times yung area gross natin na 3.375 minus yung number of holes, isang hole, 7/8 plus 1/8 times yung thickness natin na 0.75. Okay? So AE natin is equals to 0.375 minus 0.75, that is 2.625 inch squared, which is dito greater than pa din dun sa 2.414. So, ibig sabihin okay pa siya dito. Okay? Next is to calculate for slenderness ratio. So, 5.75 feet times 12 inch feet over square root of inertia natin will be 4.5 times 0.75 cube over 12 for inertia, and then yung area natin is 3.375. 3.375. So L over R natin is equals to 5.75 times 12 over square root of 4.5 times 0.75 cube over 12 times 3.375. Okay? So 318. So greater than 300. So ibig sabihin not okay. Not good siya o not okay. Okay? So sabihin, patry ka ulit. Try thickness is equals to 1.0 inches. So dito, okay, yung AG greater than 3.241 is equals to W times 1.0. W natin, 3.241 inch. Pero isay natin na um, try natin ng 3.25. 3.5 na. Okay. Okay. So, yung area gross niyan will be 3.5 times 1. So, 3.5 inches squared. Okay. Net area. So, AE will be equals to AG minus area ng holes times yung U natin. Okay. So, 1.0 times AG is 3.5 minus 1 whole is 7/8 plus 1/8 times 1.0 yung thickness. So AE will be equals to 1 times 3.5 minus 1. So 2.5. Okay, 2.5 is greater than 2.414. So okay siya for effective area. Then for L over R, so 5.75 feet, 12 inch per foot, square root of inertia natin will be 3.5 times 1 cube over 12, and then this will be yung area natin 3.5. Okay, L over R is equals to 5.75 times 12 all over square root of 3.5 over 12 times 3.5. Okay, so equals to 239, so less than 300. So okay na siya. Okay, therefore use plate na may dimension na 1 inch thick times 3.5. So, yeah. Both using Lrfd tsaka ano natin, ASD yield ng same economical section. Okay? Bakit nagkaganon? Kasi yung ratio ng dead load sa live load almost 3 times nung live load. Kaya medyo naglapit yung values, no? Pero in other cases, pwedeng mas economical sa LRFD sa kanya. Okay? So ito yung solution for problem number 1. Okay? Next. Okay, so paano naman pag hindi rectangular yung member like this one? Okay? Select an unequal leg angle tension member 15 feet long to resist a service dead load of 35 kips and a service live load of 70 kips. Use A36 steel The connection is as shown, and then use Lrfd and Asd philosophies. Okay? So we have dito, meron tayong um, angle bar na nakakonect sa gusset plate, no? Ito yung angle bar natin. We have applied dead load and live load of 35 and 70. And then yung diameter ng bolt natin is 3/4. Okay? So ano pa yung given natin? Meron tayong length na 15 feet. Okay? Ito na yung dead load, live load natin. And then A36 tayo. So A36, tama agad niya na Fy niyan ay 36 KSI. Then Fu niyan ay 50 KSI. Okay? Yung connection niya is as shown. What will be now the solution? Okay? So first is, kung LRFT muna yung gagamitin natin, okay? First is yung TU muna natin, ultimate load. Okay? So TU, gamitin ko na yung mag-govern, no? LL. Okay? So 1.2 times 35 plus 1.6 times 7. TU is equals to 1.2 times 35 plus 1.6 times 70. That is 154 kips. Okay. Next is to identify yung AE tsaka AN natin. Okay. So AG should be greater than yung TU natin all over 0.9 FY. It's equals to 154 kips all over 0.9 ng 36 KSI. Okay. So AG should be greater than or equal to 4.753 inches. Then for effective area, net area, so TU over 0.75 ng FU is 154 kips all over 0.75 ng 58 KSI. Okay? So ang AE natin should be 154 all over 0.75 times 58. So 3.540 inch squared. Okay? So yan yung limit natin. Next is to check for yung slenderness ratio required. Okay? So slenderness ratio natin is R minimum is equals to L over 300. So walang nakaspecify. Okay. So dito, ang length natin is 15 feet. So 15 feet times 12 inches per foot over 300. Cancel yung foot. So R minimum is equals to 15 times 12 all over 300. So, dapat yung radius of gyration niya is 0.6 inches ang minimum niya. Okay? So yan. So meron na tayong tatlong i-check. So ang una is gagamit na tayo nung ano natin, nung AISC construction manual. Okay? Since iba na yung section natin, no? Hindi na siya basta rectangular section. So, ang unang gagawin is yung gross section natin, 4.753. Dapat yung consider natin na dimension ng angle bar, unequal, sabi niya, unequal, no? Take note of that. Sabi niya ay unequal dapat yung leg. Dapat minimum siya ng 4.753. So, greater than dapat ng value yan. So, looking at our dito, okay. So, punta tayo sa table ng angles. Yan, table 1-7. Then going do sa pinaka last page ng angle. Yan, so ito 'yon. So mula dito, ito yung pinaka maliit na section niya. And then yung unang number lagi na naka-indicate sa kanya dito Okay? So, diba, ito yung first leg, second leg, ibig sabihin equal legs to, and then thickness yung pangatlo. Yung nasa unang pwesto lagi is yung lightest section niya. Okay? Ibig sabihin ito yung pinakamagaan, pinaka-economical para dito sa 2 by 2. Okay? So pag umakyat tayo dito sa 2.5 by 1.5, 1 by 1/4, 1/2 yung magiging kanya. Sa net area tayo titingin, no? Net area. Okay? Again, required natin is 4.75. So tingnan muna natin yung lahat ng mga lightest na section. 4.75. So ito is 2.26, so wala tayo dyan. Okay, next, area 8.5, masyadong malaki. 9.4. Area pala tayo tumingin. Hindi pala ako sa weight pala ako nakatingin. 4.5. Maliit pa to. Maliit pa. So, continue lang. Dito, ito, 5.85 to. Pero 3/4 na siya. Okay? So, try natin ng mas maliit sa kanya. 5/8. 5/8. 4.93. So, pwede natin gamitin. Pero minimum na ba yun? I-check mo dun sa iba. So, dito, titingnan mo yung area. Meron ditong 4.79. So, pwede siya. Meron siyang 4.75. Pero 753 yung need natin, no? So, dapat greater than sa kanya. Hindi na to pwedeng 4.75. Si 4.79 is 1/2 siya, pero equal angle siya. So, hindi siya pwede. Okay? Kailangan natin is unequal. So, ang i-check na natin ngayon, since ang wala nang kasunod sa 4.79 is ito, 4.93 na ang dimension is 5 by 3/2 by 5/8. Okay? So, kunin natin yung kabuuan niya. Okay? So, itong dalawang page na to, itong katapat niya, kadugtong yan, no? So, ito yung kadugtong niya. Okay? So, anong kukunin natin dyan? Yung kunin natin yung area niya, which is 4.93. Sulat ko lang muna, no? So, try natin yung L5 by 3/2 by 5/8. Okay? Yung area niya is 4.93. Sinusulat ko lang, no, para pagbalik natin sa table. And then kailangan kunin niyo yung minimum na value ng R niya. Okay? So may tatlong value ng R yan. Sa X may R 1.56, sa Y may R 0.987, sa Z may R 0.746. So yun yung kukunin natin, 0.746. Yung R niya is 0.746. Okay? Yeah. So, kinuha ko lang yung data na yon. Balik tayo dun sa ating PowerPoint. Okay. So, ito yung nakuha natin sa table. Siyempre, yung gross area is satisfied na kasi doon tayo una nag-base. Napag-check natin yung R niya o yung radius of gyration niya, greater than siya doon sa minimum natin, which is okay. Ibig sabihin, sa net area na lang tayo kailangan mag-check. Okay? So, compute natin yung net area kapag ito yung value ng angle natin. Okay? So, AE natin will be equals to U times AN. Okay? Yung connection natin is ganito yung itsura. Okay? So, ibig sabihin may dalawang pag sa rupture, may dalawang holes na dadaanan, no? Okay? And then, kailangan natin yung value ng U. Okay, wala pa tayong U. And since angle yan, tingnan natin ulit yung code. Punta tayo dun sa code. Okay, punta tayo dun sa table ng shear lag factor. Okay, dito. All tension members. So, dito, di man naka-specify kung ano yung distance, no? So, meron dito sa baba, case 8 for single and double angles. Okay? So, U is equals to 0.8. So, pwede natin gamitin si 0.8 as U. Okay? So, balik tayo. Okay? So, 0.8 multiplied yung AN natin. So, AG natin is 4.93 minus dalawang butas. Ang size niya is 3/4 volts. Okay? So, 3/4 plus 1/8 times yung thickness nung angle natin. So, yung angle natin is 5/8 ang thickness niya. Okay? So, 0.8 times 4.93 minus 2 times 3/4 plus 1/8 times 5/8. Makukuha natin is 3.069 inches squared, which is less than nung 3.54 inches na required natin dito. Okay? So, ibig sabihin, ito is not good siya. Okay? So, ang gagawin natin is to get another one do sa table. Okay? So, 5/8 tong thickness natin. Ano bang kasunod ng 5/8? Ang 5/8 is 0.625. Okay? So, kuha tayo ng another one. So, punta ulit tayo sa table. So, dun sa angle. Ayan. So, yung nag-stop tayo is dito, no? So, ang kailangan natin is yung next na area ang kasunod. 4.93 yung last natin. So, ito is 4.5, 8.0. Pag dito, yung 5.85, 3/4 na siya, so baka makapal na siya, no? Check natin baka meron sa next line na mas maliit yung thickness niya. Okay? Dito 4.63, ano mong kailangan natin? 4.753. 4.753. 4.753. Ito is 5.26 na 1/2. Tapos ito is 7/16 na 8/4. So, check natin parehas. So, pwede itong 1/2 na 7. Okay? So, again, iterative process siya. So, maganda maggawa kayo ng Excel, no? Para hanap-hanap na lang kayo ng value sa table. And then, pwede yung 7/16 kasi 5.11 to. Pero yung radius of gyration natin, baka hindi na satisfied. Wait lang. 0.866, so okay pa to. Itong mas manipis na 7/16, so 0.867, so pwede pa. Okay, so check natin yung dalawang yan. Sulat ko lang. So, try natin si 7/16 muna kasi mas magaan siya, no? 7.2 lang yung weight niya. Sa weight tayo nagde-depend, no, pag sa presyo. So, doon muna tayo sa L8/4/1. By 1, 7/16. AG niya is 5.11 and ang radius of gyration niya na minimum is 0.867. Okay? Okay. Sulat ko na din yung isa, 7 by 4 by 1/2. Area gross niya is 5.26. Okay. So R is equals to equals to 0.866. Okay. So, ayan. So back tayo doon sa PowerPoint. Okay, so ito yung nakuha. So doon muna tayo sa L8. Tawag ko itong A, itong B, no? A muna tayo. Okay, kailangan natin ng AE niya. So calculate natin. So AG natin is 5.11, 0.8, no? Na-calculate na, na-verify na natin yan. Then 2 times yung 3/4 plus 1/8 times 7/16 na thickness. Okay. 0.8, 5.11 minus 2 times 3/4 plus 1/8 plus 7/16, 3.4755. Okay. Check natin. 3.54. Okay. So, not good pa din si letter A. Si letter B, since uh, 7/16 ay 0.4375. So, pwede try natin. 0.8. So, area niya is 5.26 minus 2. 3/4 plus 1/8 times yung thickness niya na 1/2. Okay, so 0.8. 5.26 minus 2 times 3/4 plus 1/8 times 1/2 equals 3.508. Less than pa din siya sa 3.54. So not good tayo. So i-try natin, i-increase na lang yung 8 by 4. 8 by 4 by 1/2. Kasi malapit na to eh. 3.50 na. So yung area gross na to, hindi ko napakita doon sa ano. Sige. Para nasasabayan. Dito, L by 8 by 4 by 1/2. So ito yon. Okay. 5.8 yung area niya. And then yung kanyang radius of gyration na minimum is 0.863. So okay naman tayo sa radius of gyration. Okay. So going back do sa PowerPoint, ayan. So kunin natin yung AE niyan. AE is equals to 0.8 times 5.8 minus 2 times 3/4 plus 1/8 times 1/2. Okay. Is equals to 3.94. Okay, which is greater than 3.54 na. So, ibig sabihin, good na to. Okay? Therefore, use L8 by 4 by 1/2 angle bar. Okay? So, satisfied ng effective area, yung radius of gyration ay okay. And then, yung area niya, area gross, syempre, nakabase tayo doon nung maghahanap tayo. That will be okay na. Okay? So, yan yung sa LRFD. Question sa LRFD? Okay? So, if ever you have in the future, just message me, no? So, for AASD, same process din. Pero ang mag-iiba ngayon is yung value ng allowable na load natin. Okay? So, TA natin will be equals to DL plus LL lang tayo. So, that is how much? So, we have 35 plus 70. So, 105 kips. Okay? And then, yung allowable AG natin, so TA all over 0.6 ng FY, we 105 kips all over 0.6 ng FY natin is 36. So 105 all over 0.6 times 36, that is 4.861. Okay? Then AE natin will be equal to TA over 0.5 ng FU, or will be 105 kips all over 0.5 ng 58. So 105 all over 0.5 times 58, that is 3.621. Okay? Based from doon sa na-calculate natin, 3.621, hindi na papasa yung tong mga to. So pwedeng i-try na natin agad ay si L natin. Okay? For area, for effective area. Yung radius of gyration naman na required natin will not change. This will be the same for LRFD tsaka ASD. Okay? So ngayon, ito lang yung nababago pag ASD yung procedure, no? Yung value lang ng limits natin, yung minimum natin. Okay? So try natin yung L8 by 4 by 1/2. So with AG of 5.8 and R is equals to 0.863. Okay? Effective area natin will be 0.8 times 5.8 natin minus dalawa na 3/4 plus 1/8 times nung thickness natin na 1/2. Okay? So, kahit di ko pa na pala i-compute, ang lalabas is 3.94 pa din, which is greater than so sa 3.621 natin. So, okay sa ASD yung section natin na to. Pero, check natin sa table kung merong pwedeng mas magaan sa kanya, no? So 5.8 yung area niya, pag tumingin ka dito sa baba, wala nang mas mababang area na pwede, no? Bawa is sa angle bar meron. Okay? Pwede sa angle bar makakuha. Pero since unequal yung kailangan natin, dito sa equal pala to, unequal yung kailangan natin, kaya 8 by 4 by 1/2 yung ginamit natin. Okay? So, ibig sabihin sa therefore, sa LRFD, sa ASD, use din tayo nung angle bar na 8 by 4 by 1/2. Okay? So, okay. Ayan. So, same din. Use din tayo nung L is equals to 8 by 4 by 1/2. Okay? May isang procedure kung paano i-solve to na gamit yung available na table sa ibang table to dun sa AISC Construction Manual. Meron kasing kapag A36 yung material, pwede natin gamitin yung value na yon to solve para um, dun sa mag-govern na plate natin. So pakita ko lang kung paano ginagamit 'yan. Okay? So this is using third solution to using design aid na to. Ang section niya is table 5-2 of AISC. Okay? So yung requirement is kung LRFD tayo, okay? So yung calculated natin na PU is R at saka R minimum. So lagay ko na lang 154 na calculate natin na govern na TU. Okay? Then yung R minimum natin is 0.6 inch. Okay? Yung first natin is kunin natin yung lightest gross. Kunin natin yung lightest na gross area mula dun sa given nating ultimate load. So pag kinuha natin yung table dito, yung code, and then using yung D4, saan na yan? 5, 5-2. Okay, yan, 5-2. Okay, so ito yung table na yon. So pag hinanap natin yung atin, 154 kips yung atin. So hanap lang tayo ng yielding yon. Galing yun sa yielding. 154 na value, pinakamalapit na magaan. Okay? So meron tayo dito 154, 166, no? Yung value. Pero na-check na natin yan na 760 hindi pwede. So ang kasunod na is yung 188, which is ito. Okay? So ito yung value niya. So once na nakuha natin yung value na um, yung section niya, kukunin lang natin yung property niya. Okay? So, kapag nakuha mo yung light, kunin mo yung property. So, yung PU niya is 188. Pag sa yielding, okay? Yielding yung nandito. Tapos rupture is 189. Okay? So, gawin natin is kunin natin yung table, no? Yung sa property niya. So, sulat ko lang to. PU is 188 and 189. Sa yielding tsaka sa rupture. Okay? So, area gross niya is 5.8. Nasulat ko lang, no? Then area effective niya. So hindi natin gagamitin yung area effective niya. Okay? Then going back dun sa slide natin. Okay? So yung AN natin doon ay yung AE will be based dun sa 0.8 natin and 5.8. Pero syempre lalabas na greater than 154 na siya. Okay? Which is yung same na na-calculate natin kanina. This is L8 by 4 by 1 half. So 1 half. So equal siya sa 3.94. Greater than siya sa 3.621. Okay? So kung halimbawa, kung ito yung gagamitin yung method, again, for A36 lang to na steel. Okay? So kapag nag-A572 na yung steel natin, hindi na pwede yung table 5-2. Okay? Para lang sa A36 'yan. So, yung procedure nito is the same lang kapag halimbawa nag-assume tayo ng ibang section muna. Check mo ulit yung kukunin mo yung mga properties niya, kukunin mo yung net area, then i-compare mo dun sa na-calculate mo dun sa dito. Okay? Depende kung Lrfd or um, ASD yung gamit mo. Pero yun yung consideration natin. So ito pala ay sa Lrfd, 3.54 ito. Okay? So ibig sabihin okay to. Okay? So ayan. So yun yung paggamit ng ASC construction manual. So if ever hindi masyado nagigets pa, please review yung um, lecture. Then if you have question or verification, please don't hesitate to ask me. Okay? So for now, this ends our lecture, and this will be the end of the coverage for the prelim examination. Okay? So good luck guys on the examination next week, and stay safe always. Thank you.